A very good morning to our respected coordinator, Professor Sumit Banerjee sir, co-coordinator Dr. Sirendu Mahata, and all committee members, and also our eminent speaker, esteemed faculty members, and all other present over here. I, Dr. Sneha Sultana, on behalf of Dr. B.Tech Engineering College, Electrical Engineering Department, heartily welcome you all to the 7th session of AICTE ATAL-FDP program on Sustainability and Innovation in Energy, Engineering and Sensor Technology. Today, as eminent speaker, we have Dr. Kishor Bhaskarrao Nandapurkar, Assistant Professor, Department of Electrical Engineering, IIT Dhanbad. May I have the honor to read his biodata. Dr. Kishor B. Nandapurkar obtained the B.Tech degree from the Government College of Engineering, Amravati, Maharashtra in 2010, the M.Tech degree from National Institute of Technology, Calicut in 2012, and the PhD degree from IIT Kharagpur in 2020. Dr. Nandapurkar has served as an assistant manager for 3 years in NTPC Limited. He had worked as an assistant professor in the Department of Electrical and Electronics Engineering in Birla Institute of Technology and Science, Pilani, Rajasthan. He is currently an assistant professor with the Department of Electrical Engineering in IIT, that is ISM Dhanbad. Dr. Nandapurkar has published several research papers on sensor technology, conditioning in IEEE transaction. His research interests include sensor and interfacing circuit, direct digital measurement techniques, and electronic instrumentation. Dr. Nandapurkar is the recipient of Student Travel Award at IEEE International Instrumentation and Measurement Technology Conference held in Turin, Italy in 2017. Dr. Nandapurkar had secured an All India rank 14 in year 2012 in Instrumentation Engineering. He was an eminent speaker in a short-term course entitled Data Analysis for Instrumentation System at IIT Kharagpur in 2019. Thank you, sir. Now the stage is yours.
Thank you. So good morning all of you.
Good morning, sir.
First of all, thank you for the invitation. Yeah, so in today's topic, I just discuss some basics of sensors and signal conditioning circuits. At any point of time, if you have any queries, you can just ask me to stop and you can ask your questions. Okay. So as ma'am has clearly given the introduction about my research areas, I mainly work on the instrumentation aspects. So in today's discussion, I will just talk about resistive sensors and signal conditioning circuit. See, I have seen that the participants are mostly from the electrical engineering background, so I have kept the presentation as basic as possible. At the same time, it mostly covers the concept which we have learned in your second year or third year of electrical engineering, and this is common to all the specializations. So I feel that you will not face any difficulty as such in understanding the topics, although you are not from the instrumentation background. Okay, so let us start with the today's discussion. So these are just simple contents of the today's talk. So firstly, I'll introduce the sensors, and then there are different types of sensors. So in the today's discussion, I'll focus more on the resistive sensors, and then what are the challenges when you measure any quantity from the resistive sensor, that I will just discuss. And then I'll just briefly explain what is the signal conditioning and what are the signal conditioning circuits. So among the different types of signal conditioning circuits, I'll focus a little bit on the direct digital signal conditioning techniques. In that, I'll just quickly tell the dual slope based signal conditioning circuit. And after covering these basics, I'll then start with recently introduced this tunneling magnetoresistance signal sensor. This was my PhD topic, and in this particular topic I have designed two different signal conditioning circuits which are suitable for two different types of applications. So that I will discuss, followed by the concluding remarks. So all of you know that we require sensors for n number of applications. So briefly describing sensor is basically a device that responds to the quantity being measured or change in the quantity to be measured, and by doing so, usually most of the sensors are supposed to provide an output in the form of electrical, because it is very easy to process the outputs if it is in the form of electrical. Okay, there is a basic distinction between the sensors and transducer, that the transducer converts one form of energy to another form. Okay, for example, if you apply a pressure on some diaphragm kind of material, then the diaphragm will undergo some deflection. So this, you can say that the force or pressure energy is converted into displacement. So this is one form of conversion into another form. But however, in order to quantify the amount of pressure, you need to have an output which can be easily processed, and that is the reason we generally tend to prefer a device which will convert the input energy into the electrical energy. Okay, so this electrical output can be of any form: voltage, current, charge, or frequency, right? So if by some mechanism, if you can measure the change in the voltage, change in the current, change in the charge, or change in the frequency, we will be able to quantify the quantity to be measured, or the sensing variable, right? So these sensors are used in numerous applications. In your mobile phones also, we have now numerous sensors, right? So for example, if you are playing video games on the mobile phone, so in order to control the motion of a car, if you are playing some game, so there they have the gyroscopes, accelerometer kind of sensors in the mobiles, right, to control the motion of the moving object. So likewise, we are surrounded by sensors. So let us just discuss briefly the classification of sensors. Since there are numerous sensors, so of course the classification will also be in different categories. Okay, so the first one, we can say that we can classify the sensor based on the quantity being measured. So these quantity can fall in different categories. For example, thermal, chemical, electrical, mechanical, biological, optical, radiation, and magnetic quantities. Okay, so for example, temperature, heat flux can fall in the thermal category, or in the electrical, you may want to measure the voltage or current using CTs, PTs, just for an example. So that would be the electrical quantities. In mechanical, you want to measure force, pressure, displacement, linear displacement, angular displacement. Likewise, you can classify the sensors based on the quantity being measured. The another way to classify the sensor is the type of output they produce. So some of the sensors are inherently analog in nature, in the sense that they produce analog outputs, and some of the sensors can produce the digital output. Okay, for example, any resistive sensor, if you take, so just a normal potentiometer, so that potentiometer, if you are powering it with a DC signal, so the output voltage of the potentiometer is an analog. right? But if you take an example of an optical encoder, these encoders give some digital pulses, okay? So if you are measuring the frequency of pulses and all, you will be able to comment on the sharp speed. So this is one example of digital sensor. So likewise, there is one more way to classify the sensor, the requirement of external supply. So some sensors might require some supply for their operation, while some sensors may not require any supply for their operation. Okay. So based on this, there are two categories of the sensor. One is called as self-generating sensors, and the other is modulating type sensor. We have heard about the thermocouple. The thermocouple is nothing but two dissimilar metals, and if you are exposing it to two different temperatures, it will give an output in the form of some voltage. Okay. So this particular thermocouple does not require any supply to give any output. Another example of this self-generating sensor is nothing but a piezoelectric crystal, if you have heard it. Okay. So if you apply a force on the piezoelectric crystal, dynamic force on the piezoelectric crystal, it will produce a charge. Okay. So this piezoelectric crystal does not require any external supply. On the other hand, there are modulating type of sensor, any resistive sensor. Just I have taken an example of potentiometer. So this potentiometer, in order to get the output, you need to power the sensor. Okay, then only you will be able to comment on the quantity being measured. So this is the main classification of the sensor based on the requirement of external supply. Please note that in Indian context, you might have come across the terms such as active sensor and passive sensors. Okay, I am not sure. The another way to classify the sensor is whether the nature of output is linear or non-linear. Okay, some sensors are inherently non-linear in nature, and some sensors are inherently linear in nature. The relationship between the output voltage or current with respect to the input quantity depends on the type of sensor. Okay, the construction of the sensor, the basic physics of the sensor. So based on that, you can say that some sensors are linear in nature and some sensors are non-linear in nature. The examples of linear sensor include RTDs, strain gauges. Okay, but regarding the non-linear sensors, the thermistor, if you have heard about it, the NTC thermistors, so they are non-linear in nature. Likewise, the resolvers, if you have heard about it, Hall effect sensors for measuring the angle, they are inherently non-linear in nature. So coming towards the last category of classification, so these sensors, they respond to the change in the quantity. Now, what change exactly is occurring in the sensor? Based on that, there are different classifications of the sensor, and these include resistive sensors, capacitive sensors, inductive sensors, electromagnetic sensor, piezoelectric sensor, photoresistive sensor, and some sensors are designed on some specific effects. Okay. So for example, in the resistive sensors, the resistance of the sensor undergoes some variation. In the case of capacitive sensor, the capacitance of the sensor changes, okay, with respect to some measurement. As an example, you know that so far you might have used capacitor only for the filtering purposes and all. So you know that the capacitance can be given by EA by D, right? So if I have a plate, so capacitor is nothing but two conducting plates separated by some dielectric medium, right? So if I fix this one particular plate and if I apply some displacement to the other plate, what will happen to the D? This will change. This change will affect the capacitance, right? So it means that using this arrangement, you can measure the displacement, right? So at the same time, you please note that when we are saying A, this A is nothing but the overlapping area of the plates, right? So if I have an arrangement something like this, right? You please try to understand this in something in two-dimensional form, okay? And if I kind of rotate this one particular plate, the overlapping area might vary, right? So this particular concept can be used to measure the angular position of a shaft, right? So these are the basic examples by which you can introduce some change in the resistive or capacitive inductive or inductive sensors to measure one or the another variable. Am I clear here, students? Oh, I'm sorry. Yeah. Yes, I'm just habituated. Yeah. So yeah. So while we have discussed about the classification of sensors, but there are some important parameters we must look into before selecting any sensor for any kind of applications. These are basically the sensor characteristics. Okay, so if you go to market and if you want to buy some sensors, you must be sure of certain parameters. And what are those parameters? So again, these parameters are again quantified in two categories. So one is called as the static characteristics and the other one is called as the dynamic characteristics. Okay. So for the static characteristics, as the name itself suggests, when the input to the sensor is a constant, it is not changing with respect to time, then what are the different parameters we must look into so that to access the feasibility or applicability of the sensor for such applications. So these are these parameters. So the first one is the measurement range. For example, if you want to use a temperature sensor for a furnace measurement, you know that typically the furnace temperature can go up to 1200 degrees centigrade also. But if you are using a sensor which is having a maximum range of 500 and all, so you cannot use that sensor for the furnace temperature measurement, right? So likewise, you have to be sure with the accuracy of the sensor. So if I want to measure a parameter with an accuracy of 1%, you cannot use a sensor which has an accuracy of 5%. The sensor with an accuracy of 5% may cost you less, but it is not sufficient for your application, right? So likewise, there is a parameter which is called as sensitivity, which is nothing but the change of the output variable with respect to the measurement. So that is the sensitivity. Again, you have a resolution. Resolution is basically the smallest measurable input change. Okay. So for example, maybe a simple ruler, please pay attention, simple ruler, it might be the basic device which we have used in our school, right? So if you see the rulers, there are different scales marked, right? So although the range of the ruler is maybe for 15 centimeter, but that doesn't mean that you can measure any distance between 0 to 15, right? So you see that there are different markings. So the 15 centimeters are divided into say 15 slots, main slots. Again, 1 centimeter slot is further subdivided into 1 millimeter. So the resolution of the scale or ruler is 1 millimeter, right? So likewise, you may have to choose the sensor depending on the resolution. Then another important point is the linearity. Okay, so can anybody say, so these measurement range, accuracy, sensitivity and resolution we can easily quantify. How to quantify the linearity or non-linearity of a sensor?
From its characteristics.
Yeah, so see, let us take one simple example. See, I usually tend to have a lot of two-way discussion with my audiences, okay? So please take part in the discussion. Let us take a very basic example. See, suppose I have given you one simple resistor, okay, and you want to find out the value of resistance, right? So you can do it by voltmeter and ammeter method, right? You apply some voltage, measure the current flowing through it. The ratio of V by I will give you the value of resistance, right? This is very basic. Now let us assume that instead of applying only one single voltage, I have applied multiple voltages. So this is X, this is I. So the plot of this is something like this, right? But this is what the expected characteristics is. So if you are taking some finite number of readings, so what will happen is instead of a straight line, you will get some points, right? So if you see, these points may not fall on a single straight line. Am I clear here? Right? What? Yeah. So what I mean to say here is, a single line may not cover all these points, right? So it means that from here to here, the slope of the system is something else. From here to here, the slope of the system is something else. From here to here, here to here. Are you getting my point? Right? So it means that the linearity of the sensor is not exactly 100%. If the system is linear, or if the sensor is linear, the slope of the curve, input-output curve, is constant over the entire measurement range. Am I clear? So if it is now, let's say for example, there could be many reasons. For example, you are not measuring the voltage accurately, or there could be some ammeter internal resistance, because of which you may not get that exact straight line passing through origin, right? So if I want to find out the actual slope, then there is one technique which is called as least square error. How many of you have heard about it? Right? So what does this technique do is, it tries to fit a line which will minimize the square of some of the errors, right? So if I have one data point here, one data point here, one data point here, so the equation of line y is equal to mx plus c. So the m and c are obtained such that the sum of y minus yi square is minimum. That is it. And can anybody tell me why here we have considered the square of errors?
Minimize is going to become minimum.
No, but we could have taken the sum only. Exactly. So for some cases you will have a positive deviation, and some cases you will have negative deviation. So if you consider this approach, the positive deviation and negative deviation may cancel each other. That doesn't mean that the whatever the coefficients you obtain for m and c are correct. So that is the reason we take this square, right? So if you do this, you will get some equation. Now you will find that whatever the equation of this y cap, this reading of y cap may or may not be equal to the actual y you have obtained, right? So the deviation of y cap minus y divided by range of y into 100% is a method to quantify the nonlinearity in the system, right? So please note that this is entirely different from the accuracy. Accuracy will it is basically just the difference of the measured value minus true value divided by full scale range into 100%. But here it is different. Here you are obtaining the y cap considering some offset also, right? So the linearity and accuracy may or may not be same, right? For example, so many times we have seen that the analog instruments are there in our laboratory, voltmeter and ammeter. So even if you do not apply any input, it will still show some readings, maybe 5 milliampere, 10 milliampere and all. This 10 milliampere of reading might be preserved for all the values, right? So your graph will be something like this. At 0 input, you will get a reading of some 5 milliampere, right? So this doesn't mean that now there exists some error, but the system is perfectly. It's very important to find out whether the sensor is linear or not, and that is done with the help of this standard least square error method. Okay. So then you have the one more concept, which is repeatability. So the ability of the sensor to reproduce or give the same reading again and again is basically the repeatability. Okay. This basically shows the precision of a sensor. Okay, so these are all the quantities which are desired quantity. However, there are some quantities which are undesired. For example, threshold. So what is the threshold? So if you keep on increasing the input to the sensor, the output of the sensor may not change. Okay. Then after certain value of the input, the output start changing, right? So that minimum value is called as the threshold. And usually the sensor should not have any threshold. Okay. It should measure any quantity right from its lowest measurement range. Yeah, then another parameter is hysteresis. Everybody knows that. So when you are increasing the quantity, you will get some readings. And if you are increasing the quantity, the readings may not overlap or coincide with the readings which you have obtained by increasing the input, right? So the difference between these two is basically the hysteresis error. So this is once again the undesired quantity, and the another quantity is the drift. So if you apply an input to the sensor, the output of the sensor may drift over some period of time. So if you apply some input and you get some reading, after 1 hour if you come back and see the reading may be different, right? So that is basically the time drift, and it may drift because of the temperature changes also, surrounding temperature changes. So this is also an undesired phenomenon. So similar to this, there are some important dynamic characteristics. So in the dynamic characteristics, what we do is we expose the sensor with some quantities which are changing with respect to time, right? So the parameters which are important in this case are speed of response, how well the sensor responds to the change in the quantity, the fidelity, the ability of the system to reproduce or track the changes in the input is called as fidelity, and the another one is the bandwidth. Now in order to explain the concept of bandwidth, so we all have used the handheld multimeters in our laboratory to measure the voltages and all, right? So there we know that the voltmeter, if it is an AC quantity, it measures the RMS value, right? And this RMS value of a sinusoidal signal is Vm by root 2, right? Now you please note that if you derive this expression for any quantity, any sinusoidal quantity of any frequency, this function is independent of frequency, right? Vm by root 2 is an independent of frequency of the signal. So if I apply a signal of 10 Hz to my handheld multimeter, it will give some reading. The same reading I should get even if I apply 1 MHz of signal, right? But that will never happen. Right? If you have a function generator in your laboratory, you can just do these simple exercises, apply a signal of 10 Hz, 50 Hz, you will find that the RMS value will be constant for certain range of frequency, and then it will start to drop. So the actual frequency response, if you plot, it will be something like this. And the frequency at which the magnitude falls below the 3 dB is basically the bandwidth of the instrument, right? So you are expecting that your meter, that whatever voltmeter you are using, is independent of the frequency, but it is not, right? And whatever the sub parameters, whatever the different blocks of the instrument which you are using in designing the voltmeter, that basically decides the cutoff frequency. So instead of going for a normal handheld fluke multimeter, if you go for a tabletop multimeter with an accuracy of 6.5 digits, you will get the bandwidth much higher, right? It means that you will be able to measure the RMS value much accurately even for the higher frequencies. Am I clear here, students? Oh, sorry. Yeah. So anyway, yeah. So the main important point is you should learn these things. Yeah. So then another important thing is the dynamic error. Again, so if you are increasing the quantity and it is changing with time, the output may not, exactly follow the input. Okay. So because any sensor will take some time to respond. So this particular aspect will introduce dynamic error and the measurement lag in the system. Okay. So for an example, so let us assume that I want to measure an angle. Okay. So in this case, the angle, input angle, will increase from 0 to 360, and then again it will come back to 0, then again, right? So this x-axis is time, right? This mechanical rotation. If suppose this shaft is rotating continuously, it will travel linearly from 0 to 360 degree, again come back here, then again it will go to 0 to 360 like that, right? But if suppose the sensor takes some time to measure particular quantity, what will be the response? It may start from here and it may be something like this, right? So there exists a measurement lag as well as dynamic error. at this particular instance of time the actual angle is this much, but the input angle is this much, but the actual output which we got from the sensor is something different, right? So for this error to be minimized, the speed of response of the sensor must be as fast as possible, okay? And if you are from the control system specialization, these kind of delays will cause a problem in the stability of the system, okay? So whatever the dynamic error or the measurement lag in terms of time, that must be known to the user so that the control system will take care of the stability oscillations, okay?
Sir, can you explain again the second point, that is under dynamic characteristics?
The fidelity, yeah. So, for example, if suppose the input characteristics is like this, now, even if there is a measurement error or lag, but the system is able to reproduce the same output. If it is so, then I can say that the fidelity is good. Okay. For example, for an op-amp, if you apply a sinusoidal signal of very high frequency, the output of the op-amp, even if it is a buffer, okay, negative, positive, right, and this is input. So this sinusoidal input is a high frequency. What will be the output? It will be triangular waves, because there is one factor which limits this, and that is nothing but the slew rate of the op-amp, right? So it is because of some limitation imposed by the op-amp, the output is not, replica of the input, and that is basically the fidelity. So among this, let us just talk about the resistive sensor. So I mentioned that the sensors can be classified into different types. So today I will just talk about the resistive sensor. The resistive sensors have different advantages. Okay, these sensors are quite compact in nature and they are easy to design. The resistive sensors are nothing but a simple wire. Okay, so if you are stretching the wire, the dimensions will change, the resistance will change. This principle you can utilize it for measuring the force. Okay, so likewise the sensors are reliable. Okay?
So ceramics also use of resistive ceramics?
Yes. Thermistors are made up of ceramic materials. Yes, there are different types of actually materials, frankly speaking. They are not just made up of only metals, they are also made up of some semiconducting material. Nowadays there are resistive sensors which are made up of multiple layers also. So it's not necessarily that they are used of only just wire. This is just one example I have given. Okay. So the another advantage of the resistive sensor is they are reliable. So can anybody tell me how to define this reliability of a sensor? We often know the word reliable, but how do you define it in terms of sensors and all?
Every moment it will be given the right measurement.
Yeah, anyone else?
But if we repeatedly measure something and getting the same values,
Then that is precision. I can say that it is precise, right? Then precision may not be accurate, right? So usually the reliability can be defined as the ability of a sensor to perform or to measure the reading faithfully is called as reliability. Okay. How do you say reliable? If the device or the sensor is performing its intended function, right? So that we can say that it is a reliable. So the resistive sensors are basically reliable. And since most of the resistive sensors are, they require the external supply from the operation, so therefore I can say that the output sensitivity of the sensor is adjustable. And another advantage of this is that since they are just the resistance, so it can be easily integrated into the subsequent signal conditioning circuit. Okay, so I am going to cover this aspect of signal conditioning circuit in details. So. And because of these advantages, the resistive sensors are used for numerous applications. Okay, the temperature measurement using resistance or temperature detector. So they are used for many applications. For example, the bearing temperature measurements of critical drives such as mills and some big motors, pumps and all. So they are used for that. So likewise, there is one more resistive sensor which is called as force sensitive resistor. This is used in some robotic applications and in tactile sensors for monitoring the bridges and all. They are used for monitoring the structural health of the bridges constructed. And there you have now the giant magnetoresistance based sensors, tunneling magnetoresistance based sensors for current measurement and for angle measurement and so on. So for the resistive sensor, as I mentioned, the electrical resistance changes with the measurement, okay? And these resistive sensors are further classified into different types, and these classification include the single element. The examples of the single element based resistive sensor is RTD strain gauge and thermistor force sensitive resistor. The another one is differential or push-pull type. For example, a potentiometer is a simple example of push-pull type resistive sensor. The other one is the quarter bridge. I will discuss these parameters once again in detail in the next slide. So the another one is the quarter bridge sensor. The another one is half bridge sensor, and the another one is the last one is the full bridge sensor. Okay. Now let us see what are these single element based sensors. So as you can see in the diagram, the single element based sensor, as the name itself says, so as the name itself suggests, a single resistor, variable resistor, is treated as a single element based resistive sensor. Okay. Now there are certain issues with this. Okay, so this particular arrangement is called as two-wire based single element type sensor. Please pay attention. So now you see that the change in the resistance. Please do not discuss. So the change in the resistance is an indication of the applied quantity, right? So now if suppose you want to measure this, and if assume that the sensor is located far away from the signal conditioning circuit, so you will take out some wires. Now these wires will also have some resistance, right? So these resistances will get added in the sensor resistance. So the measurement will become erroneous when you do not consider these resistances, right? So how to take care of this? You can take care of this using one more wire, and this arrangement is called as 3-wire. Okay, now let us just assume that these are the lead wire resistances. Now assuming that these lead wire resistances are again kept in the same environment and they are made up of same material, can I say that the RL1, RL2, RL3 are same? I can say that, right? So if you are measuring the resistance here, can anybody tell me what is the effective resistance here? It is RL1 plus RL2 plus the sensor resistance, which is RL plus delta R, right? And if you are measuring the resistance here, what will be the resistance? RL3 plus RL1. If these resistances are equal, you just subtract the reading from here to get this one, right? So this way you can compensate the effect of lead wire resistances.
Sorry.
Yeah. So
What is delta?
delta R is the change in the resistance. Sensor, the sensor is a resistive sensor. So the resistance of the sensor will undergo some variation. It will change from its nominal value by some fraction, which is delta R. Yeah. So what I said is, when you have only the 2-wire sensor configuration, the RL1 and RL2 will affect the measurement, right? This is your sensor, R plus delta R. The delta R can be positive, negative, okay? So RL1 and RL2 will get added here. So if you are measuring the effective resistance here, this resistance is nothing but RL1 plus RL2 plus R plus delta R. Now you also have these two terminals accessible to you, and if you measure the resistance between these two terminals, this resistance will be RL1 plus RL3, right? So you have measured this resistance, you have measured this resistance. So you can subtract this quantity from here to get R plus delta R, right? So this way you can compensate the effect of lead wire resistance. Now again, of course, people.
But otherwise, sir, if the RL2 and R plus del R and RL1 is there, okay, and if I know the RL2 and RL1, initially I know the external resistance which is connected with the sensor.
No, this is not
the RL3 directly minus that resistance. Suppose RL2 is the 2 ohm and RL1 is the 2 ohm.
See, if you know, then you can do it. But if you do not know, then.
So after subtracting between the
So if
two,
I don't know,
the
then
RL
how could I consider that RL2, RL1 and RL3 are same?
That's what the assumption is. That's what the assumption is. That's what I said. Assuming that the leads are made up of same material and they have same temperature coefficient of resistance and they are kept in the same environment. See, usually a sensor is of very small size, right? So it will not be like some part of sensor is in this room and some part of the sensor in the another room and they are exposed to some different temperature environments, right? Right? It is a very small sensor. So the assumption that these lead wires are of equal dimensions, equal properties, the homogeneity is same, the temperature coefficient of resistance is same. It is a fair assumption that these these resistances are same, and that is why even if you are subtracting RL1 and RL3 from RL1 plus RL2, you may expect still the same result or the accurate result. Now of course, whatever the concern you have raised, that is why people have come up with one more configuration which is called as 4-wire resistances. Now let us see how does this method work. So if you have the please keep your phones on silent. Now see, if you know how does the multimeter work, you will be able to answer this question, okay? So can anybody tell me how does the multimeter work when you want to measure the resistance?
One common and another with the residual point.
No, but how does it measure the resistance? That's the operating principle. See,
If I measure the low resistance,
the multimeter injects a current of constant source, constant magnitude, and it measures the voltage drop across the resistance, and using the V by I method, it measures. Now let us assume that if I have connected the current source for this RL4 and RL3, okay? Now this is a constant current, okay? This is a constant current, maybe of 1 milliampere, something like that. And then you are measuring the voltage across this one, right? Now what is the typical internal resistance of voltmeter? It should be very high. It should be very high. So if this meter resistance is very high, what is the current drawn by this voltmeter? This is close to 0. So you see that this 1 milliampere current of constant magnitude is injected here, okay? And this 1 milliampere is independent of the values of RL4, RL3 and even the sensor resistance, right? So if you are injecting this and the voltmeter, if it is not drawing any current, the voltage measured by the voltmeter will be essentially the voltage drop across the sensor. So voltage or I into R plus delta R is the quantity which you are measuring. I, you know, the R and R this can be computed by V by I, right? So this is how the 4-wire method works. Am I clear here?
So in multimeter there is a
So
some
I'll tell you. So if you have a normal multimeter, then it have only 2 terminals, right? But if you go to the tabletop multimeters of 6.5 digit, 5.5 digit range, okay, it will have 2-wire method, 4-wire method.
Range started from?
Huh?
range started from?
As far as I remember, from 5.5 digit multimeter, you will have that provision of 2-wire measurement and 4-wire measurement. So this, I mean, of course, you have to pay for the price, right? With the accuracy, if you want to measure something, so you have to pay for the price, right? So I have
I
used.
was just asking the voltage, we give the higher voltage, so this part only can.
No, I didn't understand that. We are not giving any voltage, we are supplying a current.
Such a current.
So the multimeter will inject a current of a constant magnitude, and then it will measure the voltage across the two terms. Right? So V by I is anyway fixed. These lead resistances does not affect the value of I because it is a constant current source. Because it is a constant current source, right? So this way you can measure it. So likewise, in the different potentiometer, so you have, rheostat if you have seen in the laboratory. So this is basically a differential sensor or a push-pull type sensor, in the sense that you have a fixed terminal and you have a floating wiper. So if you are changing the position of the wiper, you are basically, if you supply a voltage here, this output voltage will be linearly proportional to the wiper position, right? So this is one example. If you see here, this is a differential sensor in the sense that if this resistance is increasing when you increase the wiper position, this resistance will decrease. Okay? So that is why it is called as differential or push-pull type sensor. The total resistance of the sensor is constant. This has one added advantage, that the current drawn by the sensor is independent of the sensing variable, because the current drawn by this is nothing but V by a fixed resistance, and this is constant, independent of value of displacement. Right? So this is one differential type of arrangement. There are some strain gauges also. If you are keeping it in the strain gauges on the top surface, some strain gauges on the bottom surface. So what will happen is, if the top surface strain gauges expresses the tensile force, the bottom strain gauges will experience the compressive force. So if this is increasing by a factor of del R, the lower resistances will decrease by a factor of same amount, right? So this is also one way to configure the resistive sensor in the differential mode. So regarding the quarter bridge, so a single element sensor can be configured in the quarter bridge using this arrangement. Just a second. Yeah. So here you can see that the R1, R2, R3, these are the fixed resistances, and I have a strain gauge here. Okay. So this particular, out of the 4 resistances of the Wheatstone bridge, so since only one resistance is there, which is a sensing element, so this arrangement is called as quarter bridge. And you have another arrangement which is called as half bridge. So in the half bridge, obviously there are 2 sensing elements, you can see here, and these sensing element can be present on the one side of the Wheatstone bridge, or they can be present on the opposite side of the Wheatstone bridge, okay, in the opposite arms of the Wheatstone bridge. So these are the 2 arrangement of the half bridge sensor. And then you have a full bridge sensor where all the 4 resistances are the sensing element, and they are in the push-pull fashion. Okay. So there are unique advantages of these approaches and all. You will see that this quarter bridge configuration will give a nonlinear output, whereas the depending on the type of sensor, the full bridge and half bridge sensors may give linear or nonlinear output. Now, what are the if you have any questions? Yeah. Yeah, just a second. Okay. Just a second. What is the question?
There's no question.
Okay, PPT will be shared with all of you, right? Okay, discussing towards the challenges, I think some issues.
It has to be closed and restarted.
Yes, thank you. Yeah. So there are certain challenges. Okay. First of all, as I mentioned, the whatever the change in resistor you are expecting, for most of the cases you will see that the nominal resistance of the sensor is much higher compared to the change in the resistance, right? So this parameter is a useless parameter, right? Your objective is to find out what is the change in the resistance. Then only you will be able to measure the change in the quantity, input quantity, right? So the challenge is how to extract the information on the delta R. And if suppose the delta R is very small, for example, the metal type strain gauges, if you have heard, the gauge factor is very low. So even if you apply a huge force on it, the change in the resistance may be around say 0.5 ohm or something. So we must have a provision that can detect the 0.5 ohm resistance, right? So another important thing is the inherently nonlinear response of the sensor and the self-heating effect. If you have heard, if suppose the current is flowing through the resistance, the I square R will heat the resistance, right? And if the temperature, the resistance is having some temperature coefficient of resistance, that heating will again change its resistance, right? So your delta R should or must be only be caused because of some input quantity, not because of any other quantity, right? So that is also we must take into account what is the value of current I passing through the resistor. So these are certain challenges, and of course the effect of lead wire resistance, which I have already discussed. And sometimes the bridge-based sensors require some costly instrumentation amplifier for the linearization or offset reduction. So these challenges can be addressed with the help of some efficient signal conditioning circuits. Now, in order to go directly into the signal conditioning circuits, I'll just briefly tell what is signal conditioning. Before that, can anybody tell me the definition of the word conditioning? How do we define conditioning?
Some constraints are there, no, not like that. Some constraints are there that they may not go beyond this.
Okay. So, very often, see, as we grow up, since our childhood, we are asked by our parents to do certain things, right? Maybe praying to God, or maybe washing hands when you come from outside and all. So this is all a part of conditioning, right? You are training someone to follow certain things so that your overall well-being is established, right? So in the instrumentation concept or in the sensor-related content, so the signal conditioning is nothing but the manipulation or controlled modification of the sensor output, so that the modification will make the output signal best suitable for the next stage of the signal conditioning circuit. So this is nothing but the signal conditioning, okay? So there are different stages or different operations that can come under the signal conditioning circuit. So the first one is the amplification or attenuation. As I mentioned, that the change in the resistance is very small here. So if you see, the output of the sensor may be in the form of some microvolt signal or millivolt signal. Now if I want to measure this output voltage using some ADC, right? Now how does the ADC work? So let us take one example. So if suppose I have an ADC and the reference voltage of the ADC is say 5 and the number of bits of ADC is 8. So what does this ADC do? If you have an input of 5 volt, the output will be 1, 1, 1, 1, 1, 1, 1, 1, right? If an input of voltage is 0 volt, then all the outputs will be 0, right? Now imagine if you directly feed this output voltage from the sensor to the ADC, what will happen? most of the bits will be underutilized because the magnitude of this voltage is so small, right? So the first stage of this approach will be to amplify the signal and make it compatible with the ADC range so that you will be able to see the variations in the output voltage from all the digits. Am I clear here? If suppose the maximum voltage from the sensor you are getting is 50 millivolt, so let us do a basic calculation. This we have the 8-bit ADC. See, the number of levels are 2 to the power 8, that is 256. So 5 divided by 256 is the step size by which the 1 bit of the ADC will change, right? So if suppose this particular voltage is less than this, the ADC will not change its digit, right? So you have to amplify the signal so as to, so that the ADC will detect this change in the sensor output faithfully, right? So likewise, the attenuation may be needed. For example, if you use the CTs and PTs, the output voltage from the CTs may be in the range of say 10 volt, right? But if suppose your next system is compatible only with 5 volt, you may have to attenuate it, right? So this one particular operation, amplification and attenuation, is a part of signal conditioning concept. Then another, what could be the another operations? Can anybody guess? Let it go wrong, no problem. So, filtering, right? So, see, if you are exciting a sensor with some voltage, now this voltage may have some noise, right? So when you are exciting a sensor and getting an output from the sensor, so the output will also have the noise which is present in the excitation, right? So, or otherwise, even if you are using op-amps and all in the circuit, the op-amp will also have their own noise, right? Or the resistances which you are using, they also have some thermal noise. So in such case, if you want to measure or improve the resolution of the instrument, you must filter out such unwanted noise. So this can be done with the help of filtering. And I think all of you might be knowing the types of filter, right? Low pass filter, high pass filter, band pass filter, band stop filter, right? And there is one more filter, all pass filter, but that doesn't serve the purpose in the case of signal conditioning. If it is not filtering anything, there is no point in using in the sensor application. Okay? So as an interesting fact, if you go to the medical devices and all, so usually the devices which are powered directly from the AC supply are or may have the 50 Hz noise. This is called as power line noise, right? So if I want to just filter out this noise, the medical devices are usually coupled with a filter which is called as notch filter. Now this notch filter is designed in such a way that it just eliminates the frequency of 50 Hz, right? So that all the other signals are not affected. The signals of all the other frequencies are not affected. Am I clear here? Right? So this is very important aspect, okay, when you design the filtering and all. Then another aspect is so if you are using any sensor in the control system, it is expected that the response of the sensor is linear, because you know that transfer function and all, that concept is applicable only to the linear time invariant system. So if the sensor is giving non-linear output, you cannot incorporate in the control system and do the analysis from control system point of view, right? So that is why the linearization is one aspect which is very important, okay? And the another point is the input coupling. If I want to explain this point, let me just take one example. You can keep your phones on silent mode. So suppose I have this potentiometer arrangement to measure the displacement. Let us assume that this displacement is a dynamic displacement now. It is changing with time. Let us quickly derive the output expression. B0 will be R plus delta R divided by 2R, right? I think just R into VDC. Sorry. So this will be VDC by 2 plus delta R by 2R into VDC. Right? So you see that once again, this particular term is an offset term. It is a useless term. So, and if suppose the change in the resistance is small, and assuming that we are giving some vibrations to the wiper, right? So the output will be a function of time, and the frequency will be same as that of the displacement frequency, right? So if I plot this with respect to time axis, and this is V0, you will see that it will have a DC component as well as some AC component. Now if you see, the magnitude of AC component is much smaller than the DC component, right? So if I want to process this to the next stage, either you have to use a differential amplifier that will filter out this, or you can just simply connect a capacitor and feed the output to this. So what this capacitor will do, it will block the DC component, and all the variations here will be passed on to the next stage, right? So that is why the input coupling is also important. Okay, so there are very small concepts which are very important when you, I mean, if you are from the power electronic backgrounds and all, the filters and all, the way you are choosing the parameters, resistance and capacitances, decides the cutoff frequency a lot. Okay, even the sensitivities of the filter when the parameter changes should be as low as possible, because if the cutoff frequency is changing, then naturally your output voltage of the filter will change, right? So yeah. Then another important thing is the selection of excitation. As I mentioned, the voltage, the excitation voltage or current may have certain kind of noise, so we should be careful when you choose a proper excitation signal for the sensor. And then of course the electrical isolation, which you can offer it with the help of transformer or phototransistor, that is also come under the signal conditioning aspect. Okay, so these are the basics of signal conditioning. And now these, whatever the in practice, you may have to employ one or the different operations of the signal conditionings, so that you will measure the output quantity accurately with sufficient resolution without any noise and all, and also expect a linear output. So you may have to employ one or the another or several operations which I have specified here. Okay, and those circuits are then called as signal conditioning circuit. Okay, and these signal conditioning circuit once again can be broadly categorized into two types. One is called as analog signal conditioning, and the other one is digital signal conditioning. Okay, so here the analog signal conditioning, as the name itself suggests, they are expected to provide analog output, preferably linear, because nowadays I mean, of course there are digital controllers, but still in many industries they use analog controllers, right? So they may require the analog voltages from the sensors to process or to control any parameter. So even the analog voltages are also essential. And the other part is, other aspect is the digital signal conditioning circuits. So these sensors, these circuits are expected to provide digital output, but nowadays there is one more technique which is called as direct digital signal conditioning. So here, without using any DC, you can give the digital output. Okay, so we'll see this one by one. So, just a second. Sir, I think this is the old PCB.
They use their analog signal conditioning.
Yes, yes. Can you just think this part has not come. I have my pen drive, correct? 5 months. Is there any compatibility issue?
Sir, it is available on WhatsApp group. It is shared today, no? In the
No,
WhatsApp
sir is
group.
looking for a PPTX file. I shared the PDF one.
Same.
So do you have PDF? Then you can open it.
No, I don't have PDF, but I have brought my laptop. If it is possible, that is important.
Compatibilities.
Sir, Peter, it is shared by PDF. Share is shared.
No, I think let's have the tea break now. Let me see whether tea break is there or not. By the time we
Yeah. I have brought my laptop also. Please pay attention now. So we have seen the different operations that can come under the signal conditioning umbrella. So there I have mentioned that if you are implementing one or more operations for a sensor, then we can call whatever those implementations as signal conditioning circuits. And we can classify the signal conditioning circuit in two types: analog signal conditioning circuit and the digital signal conditioning circuit. As the name itself suggests, the analog signal conditioning circuit render analog output, preferably linear, and they are suitable for the analog controller. Please do not discuss now, okay? Whereas the digital signal conditioning circuit, renders the digital output and they are suitable for the digital controller. Nowadays, there is direct digital measurement technique also that can be utilized to obtain the digital output from any analog sensor. Okay. So, coming towards the analog signal conditioning circuit, let us just take one simple example of a quarter bridge. So here I have taken one example in which there is only one sensing element out of 4 elements of a Wheatstone bridge. So, if you find out the expression of the bridge output, first of all you have to understand that this bridge output is a differential in nature. Okay, it's not the single-ended signal; it is a differential signal. Okay, so the value of voltage Vs can be obtained by finding out the potential at the positive terminal of the bridge and the potential at the negative terminal of the bridge, and taking the difference will give you the value of Vs. That is the differential output. So if you just apply the basic voltage division principle here, you will get the Vs in the form of something like this. So here you can see that the differential voltage Vs is directly proportional to del R, but also unfortunately there is one term in the denominator, right? So the term in the denominator makes the differential output non-linear. Okay, if and only if the value of delta R is much smaller than the 4R, then we can consider the expression of Vs as a linear one. Otherwise, it is a non-linear quantity, right? So, what are the issues with this approach? So, this particular arrangement gives non-linear output. The Vs is small in magnitude, and in order to amplify the output, you require a differential amplifier. You cannot implement a single-ended non-inverting or inverting amplifier. Okay. So, how to address these issues? Okay. So, this can be addressed by using a simple technique, which is shown here. Okay. Now, here what I have done is I have used one low-cost op-amp, and the sensing element is placed in the feedback path. Okay. So, if this is the arrangement, then what will be the output voltage Vp? Can anybody tell?
What's that?
What will be the output voltage, expression of output voltage? Hmm? No, the output voltage VP, the op-amp output voltage, right? What will be the expression of output voltage? If you see this particular arrangement, just a second.
VR minus V0?
No, you see this particular, you are supplying the bridge with some positive reference voltage VR, and this particular arrangement forms a non-inverting amplifier, right? Isn't it? It is just drawn in some different fashion, but otherwise if you see, the circuit is something like this. Right? So the output voltage will be, VP will be minus RS by R into VR. Right? Now please don't get confused, okay? You may see or you may say that the right half side I have two resistances and it is connected, so the VP will get affected by because of those two resistances. It will not be. It will not be. You have to understand the basic operating principle of operational amplifier. The operational amplifier, when configured in the negative feedback, will give an output such that the voltage at the positive terminal and the voltage at the negative terminal are same. In this case, it is ground, so it is called as virtual shorting and all that. I will not go into the detail, right? So it doesn't matter even if there are some two resistances connected here. This output voltage, please do not discuss. You can ask me to stop, I will clarify, okay? So this particular output will be solely dependent on this non-inverting configuration, right? Now, if it is so, what will be the expression of V0 then?
VR minus VP by 2.
So this is nothing but, see, this is a linear system. The resistances are passive. In order to find out the V0, you can just simply apply the superposition theorem, right? So I have two signals, please pay attention, I have two signals applied to a half bridge, right? And if I want to find out V0, I can write this V0 as V01 plus V02. V01 is the output when you consider only VR. V02 will be the output when you consider VP alone, right? So this V01 will be, when you consider only VR, it will be, since these resistances are equal, it will be VR by 2. VR by 2 plus PP by 2. That's it, right? We have already expressed or obtained the expression of VP. So if I do this calculation, you will get the expression of VP which we have obtained just now, and then the V0 as I derived just now, VP plus VR by 2, and if you substitute the values of VP here, you will get the output voltage minus delta R divided by 2R into VR, right? So just by intelligently placing an operational amplifier, you have converted a non-linear output into linear, right? But still, we have not solved the issue of amplification, right? Now, you please note that this signal V0 is now a single-ended signal. So if you want to amplify this single-ended signal, you can go for a low-pass non-inverting amplifier. So you can just place a non-inverting amplifier to get the expression of V0 dash as 1 plus RF by R1 into V0. So that will amplify the sensor output. You can choose the values of RF and R1 as per the requirement, and then you can obtain a linear output. Is this clear, students? So the entire particular, whatever the approach we have followed, it consists of two operations, the bridge linearization and the amplification. So this particular approach we can call it as a simple analog signal conditioning circuit for a quarter bridge sensor, right? And if you want to obtain a digital output, you can easily feed the output to any ADC to obtain the digital equivalent of the signal, right? So this is how the typical approach of analog signal conditioning circuit is. And even if you want to place a filter or something like that, you can place at the output V0 dash side. Okay, low pass filter, high pass filter you can utilize there so as to minimize the noises in the sensor output. So this particular analog signal conditioning circuit, if you just keep one ADC at the end, you can call it as a digital signal conditioning circuit. Okay, but there is one more method to obtain the digital output without using any dedicated ADC ICs, and that is called as direct digital signal conditioning circuit. Okay, so we will see this now. I want all of you to pay attention. Okay, so this direct digital signal conditioning techniques, they render the digital output without using any explicit ADCs ICs. There are different methods, okay, by which you can obtain the digital output using this direct digital approach, and these outputs include use of the sigma delta, dual slope and its subclasses, the relaxation oscillator, direct microcontroller interfaces, pulse width conversion. Okay, I'm sure you may say that the dual slope of the sigma delta approach is also an analog to digital conversion approach, but these approaches can be easily integrated in the sensors and you can independently build without using any explicit IC. Okay, that is why I am calling these two approaches also as a direct digital signal conditioning techniques. So let us discuss a very basic dual slope based signal conditioning circuit. Okay. Now I think many of you might be knowing how does this dual slope based circuit works. Okay. So this dual slope, as the name itself suggests, it works on two slopes. Okay, that is why the name has come as dual slope. So in order to operate this, what is the circuit consist of? It consists of one integrator which is formed using the resistances RICI and op-amp, and the output of the integrator is fed to one comparator, and the comparator output is fed to a microcontroller. Okay, so if you want to measure some output voltage coming from a sensor Vx, usually the dual slope circuit consists of two modes. One is called as the integration mode and the other one is called as de-integration mode. So during the integration mode, what does this microcontroller do? It places this switch at position 0. This is a switch, okay? You can just buy this IC in the market. It is a CMOS switch IC. It's called a single pole double throw switch. It has two input and one output. Okay? So depending on the switch position, the switch output will be either be Vx or it will be minus V reference. Am I clear here? So, assuming that we want to measure the signal Vx, so we have placed the switch at, what it will do is it will place the switch at position 0 for a predefined period of time. So, when this DC signal Vx is linked with the integrator, what will be the current flowing through the resistor? Can you tell? Again, you see that the op-amp is configured in the negative feedback. So this voltage is same as that of this voltage, right? So the current, integrating current will be nothing but Vx by Ri, right? Now this constant current will charge the capacitor, right? So this capacitor, and since it is a, you see that the current is flowing from this fashion here. So naturally, the output voltage here should be lesser than this one, right? Right? So the output voltage will be negative, right? So the exact expression of this output voltage towards the end of integration can be obtained using this relationship minus 1 by RICI Vx, right? So if I just plot this waveform, the integrator for a positive input voltage will start integrating in the negative fashion. It will reach here. So after the fixed period of time, what the microcontroller will do? It will place the switch at the position 1. Now if the polarity of this reference voltage is opposite to that of Vx, what will happen to the current then? The current will flow now in the opposite fashion. So if the capacitor is charged to some level, now it will discharge, right? So this discharging will raise the voltage of the capacitor in the positive fashion, right? Now, when these integrator voltage will try to cross this zero line, what will happen to the comparator? The comparator output will be positive here, right? Because it is a positive comparator. So this particular, if you see the transition from 0 to high, this transition will be detected by the microcontroller using this comparator output, and it will stop that phase. And then once again, it will repeat the same process again and again and again, right? So if I write the expression of the deintegration, the charge balance equation, if you see the entire process in the charging phase or the integration phase, the output is starting from 0 to some value and then again it is coming to 0, right? So what is the net charge accumulated across the capacitor at the end of the integration? It is 0, right? So this is why I can write the charge balance equation as here. So I can obtain the expression of the input voltage in terms of the reference voltage, deintegration time and the integration time. So if you are measuring the voltage Vx, you can find out the quantity being measured. Am I clear here, students? So here, so once you measure the value of Vx, here it is assumed that you know the value of reference voltage. And this is a very fair assumption because in any ADC, it is assumed that the reference voltage is known to the system or the processor, okay? So we need to define this value in the microcontroller, and then just by measuring the deintegration time, you can comment on the value of the unknown voltage Vx. So if you are measuring the unknown voltage Vx, you can measure the sensing variable also, right? So now let us integrate this circuit into some actual sensing application. So I have taken one example of the differential potentiometer, right? So if suppose now I want to measure the voltage Vx and comment on the value of x, what can we do? Okay, let us do this basic exercise. So here what I have done is, the output voltage from the sensor will be x into RT divided by, that will be proportional to the value of x, right? I have just applied some voltage division principle and got the expression of Vx in terms of the displacement. This x can be anything from 0 to 1. Okay. Now please note that whenever you are processing the signal, sensor signal, so it should not only be the voltage output, but it should also be the output impedance of the sensor, right? So can anybody tell me what will be the output impedance of the sensor? See, please pay attention, okay? This is very basic and important fact. So let us assume that this is R minus delta R, R plus delta R, right? So you got the expression of output voltage, but now you please note that there are some resistances associated here. So the output voltage will also have some resistance. How will you find out that resistance? That resistance can be found out using the Thevenin's theorem. Thevenin's theorem, right? So you have found out, now whenever you are measuring this voltage, it is basically an open circuit voltage. This open circuit voltage is nothing but this resistance divided by sum total resistance into excitation. But whatever this circuit can be simplified into Thevenin's equivalent if you find out Thevenin's resistance. For finding out the Thevenin's, you know that you need to short this one and find out the net resistance between these two terminals. What will be the net resistance between these two terminals? The parallel combination of these two resistances, right? So the entire circuit can be equivalently modeled. Right? So it means that you are not just feeding the output signal V0 to the next part, but you are also feeding some impedance, and that you cannot ignore. Am I clear here? So if so this is what you get, the Thevenin's equivalent impedance, and if you now feed the same circuit to the dual slope circuit, now what are your observations? Do you think that we will be able to faithfully measure the value of Vx? Because if you see, the value of Vx is directly proportional to the x, which is displacement. Am I clear here? Right. Now if you see this particular model, equivalent sensor model, it is Vx and some RTH. Right. Now can you tell what is the input resistance while charging the capacitor and what is the input resistance while discharging the capacitor? Is it the same?
No.
Right? So here you can see that during the integration phase, the net resistance offered by or seen by the integrator is Ri plus RTH. What about the deintegration phase?
Only
Ri.
R.
Right? So this particular problem introduces error in the measurement. Okay? So this is what the modified charge balance equation will be. And you see now this Vx, this whatever this term is, this is an undesired term. Right? So this whatever this problem has come, this is basically because of the loading effect. So when you connect some next stage, this voltage Vy, ideally it should be Vx, but it is because of some drop across this Thevenin's resistance, it is not Vx. Right? So now how to solve this problem? You can just simply add a buffer in between. Right? So if you add a buffer, what are the properties of buffer? Yeah, that is okay. But here in this context, what is the property?
Impedance will change.
Yeah. So here, if you see, if you are adding a buffer here, what is the current flowing through the RTH? It will be 0 because it is a non-inverting amplifier and the op-amp offers infinite input impedance. So the current flowing into the op-amp is 0. Right? So if the current flowing into the op-amp is 0, what will be the voltage drop across the RTH?
Vx,
0. Right? Voltage drop across RTH. That RTH drop is 0. So the Vx, the output of the op-amp, will be same as that of what the sensor output is. Right? So in this case, now if you see the modified equation, now there is no question of RTH in the charging and discharging phase. Right? So this way you can faithfully reduce the effect of loading and still accurately measure the quantity. Right? So these are the small things which you must look into while designing any signal conditioning circuit. Is it clear, students? So yeah. So and of course, if you see interestingly, if you see the expression of X or the input voltage, it is independent of Ri and Ci. Okay. So that is one thing. So even if you are employing this circuit in some environment where the Ri and Ci will change because of the temperature fluctuation, this will not affect the output. Right? Because it is changing both in the integration phase as well as in the deintegration phase. So this effect Ri, Ci will get cancelled. So equal variations during the integration and deintegration will get nullified because of this approach. Okay. So this is one important part. So this was all about the very basic aspect of resistive sensors and signal conditioning. So let us now start with the main topic. Okay. This is related to the tunneling magnetoresistance angle sensor. So this is what the topic which I got using my PhD. See, angle sensors are used in numerous industries for different applications. Okay. So one of the best example is they are used in automobile industries to monitor the steering wheel positioning. Now one might feel that what is the need of monitoring the steering wheel position. So these days you might be knowing that the vehicles are coming with some electronic power steering, or it has a very good control system, right? So suppose you are driving a car on a highway, the steering wheel should be as rigid as possible, right? Because even a small minor jerk to the steering wheel may cause the accident, right? So what does this angle sensor and the control system consist of? It consists of a sensor and a signal conditioning aspect which will detect the rate at which we are rotating the steering wheel. Okay, so this feedback together with the actual speed of the vehicle will tell the system that we are now running on a highway, right? So it will try to make the steering wheel as rigid as possible so that such accidents cannot happen. On the contrary, if you see the parking and all is high, right? So what it will do in that case, the control system will make the steering wheel as free as possible so that the whoever is riding the vehicle will have the flexibility to turn the steering wheel or control the vehicle properly. So this is one such example of angle sensor where it is required in the vehicle stability and all.
Is there any predefined speed for highway, predefined speed for some limit?
Yes, of course, some algorithm must be there. I am exactly not sure of it. I just want to convey the importance of angle sensor in such applications. Yeah. So, so these are the typical applications of the angle sensors. They are used in numerous applications. Okay. So coming towards the actual working of the TMR sensor, let us just disintegrate the entire term tunneling magnetoresistance into three parts. The magnetoresistance, how do you understand the term magnetoresistance? Can anybody tell what could be the magnetoresistance concept? The resistance which can undergo some variation because of some magnetic effect. Is it okay? Right? Regarding the tunneling, I think everybody knows what is tunneling, right? So the electrons are supposed to not travel in the insulator, but if you reduce the thickness of the insulator to a very small value in the range of some nanometer like that, and then there is a possibility of tunneling of electrons from one part of the layer to the other part, right? So it is a quantum mechanical concept. So this is what the operating principle of tunneling magnetoresistance is, and these sensors have numerous advantages. Some of the advantages are highlighted here. Now, to understand the working principle, the resistance of the tunneling magnetoresistance sensor changes with the direction of the biasing magnetic field. So if you change the magnetic field, the resistance will change. Now the question is how to utilize this principle to measure the shaft angle. Okay, so this is achieved with the help of a simple technique which is shown here. Okay, so this technique consists of a magnet which is attached to one end of the shaft and the angle of rotation of the shaft which I am interested to measure. Okay, so the magnet must be diametrically magnetized. So when the magnet is diametrically magnetized, so what will be the magnetic field? It will be something like this, right? So it means that the plane of the magnetic field will be parallel to the magnet, right? So the sensor TMR-IC is also placed below the magnet such that there is a sufficient area between the two. This makes the system contactless, right? So now internally this IC consists of 4 internal resistances, okay? And these 4 resistances form 2 half bridges. One consists of RS1 and RS2, the other consists of RC1 and RC2. Now all these 4 resistances, I have marked an arrow which indicates that all these 4 resistances undergo variations with respect to the direction of the magnetic field. Okay? Now in order to understand the exact working, please pay attention. So the internal structure of a single TMR element, for example RC1, which is shown here. So it consists of 3 layers. The bottommost layer is called as field layer, and the middle layer is called as insulation layer, and the upper layer is called as free layer. As the name itself suggests, the magnetization of free layer is free to rotate with the direction of the magnetic field. Okay? Whereas the magnetization of the bottom layer is always fixed in one particular direction. Right? So, if suppose if I am rotating the shaft by an angle of theta, then the free layer magnetization will always try to align with that. So, the angle of shaft rotation will be same as that of the net angle between the magnetization of free layer and the magnetization of fixed layer. Am I clear here?
What
Okay.
what is IL?
Insulation layer. So these two layers are separated by an insulation layer of very small thickness. Now that's what I said. So before the TMR sensor, there was one more sensor for which the scientists have been awarded Nobel Prize also, and that is basically giant magnetoresistance. So in the giant magnetoresistance sensor, instead of one insulation layer, there is one conducting layer. That's it. That's the only difference between GMR angle sensor and the TMR angle sensor. So what's the benefit of having the insulation layer? The resistance of the device is much higher because you are adding an insulation layer, right? So when you have a higher resistance, what about the power consumption? Power consumption will be lower.
Lower,
Right? Right? So the MR based sensors, magnetoresistance based sensors are widely used in the aerospace applications. Where if you are sending an aircraft to some space and all, so your power consumption should be as minimum as possible, right? So the sensor should be compact in size, it should be light in weight, right? So that the fuel consumption can also be minimized if you are using a small sensors, right? So that's why the MR technology is used in many such aerospace applications. So coming towards the main point, so the magnetization angle between the two layers is governed by the shaft angle, right? And it is because of the tunneling effect, the electrons tunnel literally from the lower portion or to the bottom portion or vice versa. So the net resistance, it has been observed that this net resistance of the TMR device or single element is a function of shaft angle. Now if you see this resistance, it is a cosine function of the shaft angle. Okay. Now I have one question to all of you. So if suppose
It's equal to means it's equal to f theta or proportional.
so it is a function of theta.
Function
It
of
is a function of theta. Okay. So my question is, if suppose I have a quantity which is varying as a cosine function, okay, and this is with respect to the shaft angle. This is 180, 0, 360. This is resistance. Can you tell me what is the maximum value of theta which we can measure using a single transfer characteristics?
But sir,
No. You see this transfer characteristic. This is the sensor response. Okay. My question is, what is the range of the sensor by which we can measure the value of theta very accurately? Can we measure from 0 to 360?
0 to 180. 0 to 180.
So you cannot measure from 0 to 360. You see, from here to here, the response is unique, but after this, the response is getting repeated. So if you are getting an output from this, and if suppose the resistance is somewhere here, you will not be sure whether the angle is this one or the angle is this one. Am I clear here? Right? So you need to have some other provision which facilitates the measurement
360.
up to 360 degree, right? So here internally these resistances are intelligently placed in this fashion. Okay, now you see that the two TMR sensors are placed such that their fixed magnetization is displaced by 90 degree. Okay, so if the fixed magnetization is displaced by 90 degree, if one is varying as a cosine function, what will be the other function? It will be a sine function. So it will be something like this. Now if you see the response, for any value of theta, there will be unique combination of this resistance and this resistance up to 360 degree. So it is because of this particular approach, you can measure angle up to 360 degree. Is it clear? Right? And obviously you can also see that there are two more elements. These green arrows marks the magnetization of fixed layers, okay, of the respective elements. So you see that there is a 180 degree phase shift between this element and this element. So if one is varying as a cosine function of theta, the other will vary as a cosine function of theta but with a 180 degree phase shift, right? So similarly, if this is varying as a sine function of theta, this will also have a sine function but will have 180 degree phase shift. So it is because of this unique arrangement, the exact resistances follow these particular equations. You can see that the one is varying as a cosine function in a positive direction, the other is varying in a cosine function in the negative, likewise for the sine bridge also. So these are the actual resistances of the TMR sensor. They just follow the sine and cosine relationship, right? So again if you see the total resistance of this 1/2 bridge, RS1 plus RS2, what will be the value of RS1 plus RS2? This will be 2Rn, right? You see the equation number 1, right? Again, that bridge resistance, as I was talking about the potentiometer case, that bridge resistance is independent of the value of theta. So the current consumption is independent of theta, right? So this is one unique advantage, that this push-pull arrangement keeps the total bridge resistance constant and it is independent of theta. So the current is not governed by shaft position, right? So now the question is, how to measure the value of theta? So now you can see, if you just apply the please pay attention now. If you apply the excitation signal here, and if you substitute the values of RS1, RS2, RC1 and RC2, you will get the expression of the equation number 2. So here you will see that there is one offset term, okay? So this particular offset term is only because the sensor is basically in the half bridge fashion, okay? Now you can see that there is a one fixed offset which is proportional to half of the excitation voltage. So there is one more type of sensor. Whatever I have discussed so far is a half bridge sensor. There is one more type of sensor which is called as full bridge sensor. So the full bridge sensor internally consists of 2 elements of sine fashion. You will have 4 elements of sine fashion. This is increasing, this is increasing, this is decreasing, this is decreasing. So likewise you will have one more bridge. So you will have Rn plus minus delta r sin theta, Rn plus delta r sin theta, Rn minus delta r sin theta, Rs plus delta r sin theta, right? So this differential output will not have that offset term of 0.5 dx. Is it clear? The very basic mathematics, okay? There is nothing rocket science here. So the differential outputs P sine and B cos will not have any offset here, okay? So nevertheless, if you see, in both cases the output is nonlinear in nature, right? The sine and cosine functions are nonlinear quantities, right? So the question is how to measure the value of theta using such nonlinear nature outputs. Now can anybody tell me? I will not discuss any solution right now, but if suppose you were given this challenge, how will you measure the value of theta?
For small theta, sin theta is equal to theta.
That is one small signal approximation, but then you will not be able to measure till 360 degree, right? See, you only have 2 signals. V sine is equal to Vm sin theta.
Square will square, sin square plus cos square.
But that will be 1 only, right?
Theta is going. Tan theta.
By tan theta.
Exactly. So if you divide these outputs, V sine by V cos, you will get tan theta. So the theta will be inverse tangent of V sine and V cos, right? So this is a very straightforward approach, okay? So this is, you please remember one thumb rule, that if you have any sensor which is having a nonlinear response, the best way to linearize the sensor, or the easiest way rather to linearize the sensor, is to implement an operation which performs inverse of that operation. For example, the thermistor varies exponentially. The resistance of the thermistor varies exponentially, right? So if I want to get a linear response, you can perform the natural logarithm on this operation, right? So likewise, if I have a resistance which is varying as a 1 by x, you take the reciprocal of this to get an output proportional to x, right? So here also you can obtain the linear output if you implement the inverse tangent operation on these 2 signals. So let us see how the circuit implementation of the inverse tangent operation is realized, okay? So now before that, please note that the sine and cosine nature outputs are not only obtained from the TMR sensors, but there are some other sensors also. Resolvers you might be knowing. there are some capacitive encoders, and then there are some nonlinear potentiometers, Hall effect encoder. They also render similar type of sine and cosine natured response with respect to the shaft angle. Now let us see the first signal conditioning circuit, which will give the direct digital output without using any ADC. So this is a very basic schematic of the proposed arrangement. So here you can see that the TMR angle sensor IC, it is powered from a quadrature oscillator. Okay. So what is a quadrature oscillator? It is an oscillator which produces two outputs, and these outputs are supposed to be phase shifted by exactly 90 degrees, and hence the name quadrature shifted. Okay. So, and the outputs of the sensor then are given to one summing amplifier, one differential amplifier, and one phase detector block. Okay. So whatever the signal conditioning which we have designed here, this signal conditioning circuit is immune to the parasitic capacitances of the sensor as well as phase error of the quadrature oscillator. Okay. Now let us just see the methodology of the circuit. Okay. Now ideally, as I mentioned, the quadrature oscillator outputs are supposed to be phase shifted by exactly 90 degrees, but we don't live in an ideal world, right? We live in a practical world. So instead of 90 degree, these outputs could be shifted by 89 degree, 91 degree, 92 degree, like that. So under such case, the exact output expression of the practical quadrature, they are given by this expression. So where this term phase psi represents the phase error of the quadrature oscillator. So under such cases, the TMR outputs can be given using these expressions. Okay. So please pay attention. This is a very basic mathematics. So if you so if you have these outputs, you can see that these outputs are basically amplitude modulated. You have a signal which is varying as a omega frequency, but depending on the value of theta, its amplitude is changing. Okay, same is the case with the sine signal. So if you add the two signals here, Vm cos omega t cos theta plus this one, so you can simplify this using basic trigonometry, and you will get that the resultant signal is phase shifted by an angle phi. Okay. So if I draw the phasor diagram of this, so if I substitute the ideal value of phase phi, this phase shift phi is nothing but the sensing angle theta. However, if the phase error phi is not exactly 0, then under this case the phi will be less than theta. This is a very basic mathematics. Okay, you can verify this. So let us see. So here we have taken the addition of these two signals. Okay. So if we take the subtraction of these two signals, you will get an expression of resulting signal as Ka Vm cos of omega t plus phi 2. So if you do this again, the mathematical analysis and the expression of phi 2, you will get the equation number 2, and the phasor diagram of this will be shown here. So this phase phi 2 will be greater than the sensing angle theta. Now you can recall the previous case. You have the phi 1 less than theta and phi 2 greater than theta. So you can take out the average of phi 1 and phi 2, so that the average of phi 1 and phi 2 will be close to the sensing angle theta. So I can define a compensation function such that the phi 1 and phi 2 by 2 will be close to the sensing angle. So if you substitute the expressions and simplify using the tan inverse of A plus tan inverse of B, you will get an expression as per equation number 3. Right? So here, if you see the cos phi term, if you plot the nature of cos phi, the cos phi is something like this. So here the cos phi will not change much, right? It will always be 1. So if it is always be 1, what will happen to equation number 3? This cos phi will always be 1, so half of tan inverse of tan to theta will always be close to theta, right? So this mathematical analysis was analyzed in terms of the error. So you can see that the error in this equation number 3 is very less even if the phase error varies from plus to minus 5 degree. Means that you can even have a phase shift between the sine and cosine related output from 85 to 95 degree. Still, you will have very less error in the output. Okay. So this is about the measurement methodology, but what about the circuit implementation? So the circuit implementation, there are two ways to measure the theta. This is the combined phasor diagram. You have a phase phi1 which is lagging the reference signal, and you have a phase phi2 which is leading the reference signal. So you can measure phi1 and phi2 one by one, or you can directly measure the total phase shift between phi1 and phi2. Right? So in this work, I have just designed a circuit which will measure the total phase shift between the signal phi1 and phi2. Okay. So regarding the circuit implementation, you can easily employ a Zor based phase detector. How many of you know that this Zor gate can be used as a phase detector? Phase detector. Okay. So Zor gate is a basic logic device which can be used to detect the phase between two signals. Okay. So here also I have used the same thing, that these outputs are compared or converted into the digital equivalents and they are fed to the Zor gate. So, and we have used a microcontroller here to perform the piecewise linearization, and the final output varies linearly with respect to the shaft angle. Okay. So this was the measurement setup on which I have done the experiment. So this is the complete sensing arrangement of the TMR sensor. You can see that the sensor is placed here, and there is a shaft, and in this socket there was a magnet placed. Okay. This stepper motor was used to analyze the dynamic response of the circuit. Okay, what will happen if the shaft is rotating continuously with some speed? So these are the results. The final output varies linearly with respect to shaft angle for complete 360-degree range. Of course, no system is perfectly linear. Okay, you have certain non-linearities, and the non-linearities are also identified with the help of that least square error fitting, which I have already explained, and it was found around 0.25% and all. The 0.25% of nonlinearity is sufficient for many automobile applications. Okay, so we have also seen the dependency on the phase error. So here we have seen that the output is insignificantly dependent on the phase error of the quadrilateral oscillator. Here the nonlinearity remains low for all the values of phase error considered, but in the earlier approach it is found to be dependent on the phase error values. Also, we have carried out one study that the entire measurement of shaft angle, it is based on the fact that the TMR IC is exactly positioned below the magnet. In practice, there could be some horizontal misalignment or there could be some vertical misalignment in the sensing unit, right? So this was also analyzed, and we have found that the misalignment should be kept below 0.5 millimeter for the accurate angle measurement. So this work was published in two journals also, and these are the consolidated features of the proposed instrumentation system. So whenever you design an instrumentation system, you are supposed to identify all these parameters. Okay. For example, what is the type of output, what is the operating range and resolution, what is the nonlinearity, what is the conversion time, and what is the, there are different qualitative parameters also, whether there is any effect of hysteresis. The end user can see it as a specification or the data sheet. So yeah, so this work was published in two journal papers and one conferences. So of course, this entire work was based on the fact that we have gone for only the static measurement. And in order, there are many applications where you need to measure the shaft angle when the shaft is continuously rotating with some speed, right? So this particular work was found to have certain limitations for the dynamic tracking, and therefore we have developed one more circuit which is suitable for the dynamic angle measurement. Okay, so let us. I'll not take much time now. Maybe 10 minutes I'll take. So this is the linear direct digital converter suitable for the dynamic measurement. So this particular circuit does not require any quadrilateral oscillator for the excitation. Okay, so this requires only the DC excitation, and the outputs from the sensors are fed to one particular block which is called as high sensitivity signal selector, and the other block is called as SLD block. Now let us see the working methodology of this circuit. Now if you see the transfer characteristics of the TMR sensor, you have a sine and cosine related outputs, right? So you will see that for certain angles the sensor outputs are highly sensitive. For certain angles the sensor outputs are having low sensitivity, right? If you can see that the slope of this curve is high in this region, but in this region the slope is very less, right? So the slope is nothing but the sensitivity. So if it is so, it has been observed that if you process the outputs only belonging to high sensitivity region, then you can ensure the accurate measurement. Now how to select the outputs only belonging to high sensitivity region? You can do that with the help of one window detector circuit, and if you do that, you will get an output something like this. Here you can see this output is nothing but the output belonging to the high sensitivity region. From here to here, then again from here to here, and then from here to here, right? So this is the high sensitive output. Now our objective is to measure the high sensitive output, the shaft angle from this signal. Now can anybody again tell me, is it possible to measure the shaft angle up to 360-degree range using the same signal? Again not possible, because the response is repetitive, right? So you need to have some certain additional signals that will facilitate the complete full circle measurement. But before going to that point, you see that there is a discontinuity at this region and at this region, right? So we have found that this discontinuity will not pose any problem when we want to measure the static angles, but if the shaft is continuously rotating with some speed, these discontinuities will affect the dynamic measurement. Now how to get rid of this discontinuity? That is achieved with the help of one modified high sensitivity signal selector block, and the output of this signal selector block is now found to vary smoothly with respect to the shaft angle for 360 degree. You can see that now there is no sudden discontinuities, okay? So, but again, for this signal also you cannot measure the shaft angle up to 360 degree using the only one signal. You need to have additional signals also. So that is done with the help of this sinusoidal to linearizing digitizer block, okay? So we have found that if we feed the reference sinusoidal signal here to an instrumentation amplifier and the high sensitivity signal to this block, we can obtain a piecewise linearly varying characteristics. This is a perfectly piecewise linear curve, okay? And the linearization is done on this piecewise linearly varying signal with the help of some additional signals which include d sine, dt and d cos, and the final output varies linearly for complete 360 degree range. Okay? Now this was not the main objective of this work. The main objective was to measure the dynamic input. So it has been found that if the shaft is rotating continuously with some speed, the sensor output or the mechanical angle is represented using a sawtooth signal, and for these outputs the TMR outputs will vary as a sine and cosine with respect to the shaft speed, and the frequency of the sine cosine will be same as that of the frequency of the shaft rotation, okay? So these signals, when fed to the circuit, we have found that we will be able to measure the angular position of the shaft for speeds up to 1200 rpm, okay? So this 1200 rpm is sufficient for many applications, for example electronic power steering and all. So this is where the merit of this work is, that it is not only suitable for the static measurement, but it is also suitable for the dynamic measurement up to 1200 rpm speed, and this can be useful for the commutation of the BLDC motor. So this work was also published in one journal, and these are the performance specification features of the proposed developed the signal conditioning circuit. So concluding remarks, of course you not only require some sensors, but the suitable signal conditioning circuit is very essential in order to faithfully measure any quantity. So there are certain factors we must look into while designing the signal conditioning circuits. These includes the targeted application where you want to utilize the measurement system, the measurement range, accuracy, resolution, bandwidth, as I explained, if you want to go for the dynamic measurement, speed of response, and the ability to withstand the variations in the surrounding environment. So you have to look into these factors whenever you choose any sensor and the signal conditioning circuit. Okay, so this is all from my side. If you have any questions, you can ask me. Thank you, all of you.
Thank you, sir.
Sir, in EMR sensor you are using this biasing magnet. Okay, so can I try that? If we increase the number of biasing magnets to 2 to 4, is there any effect on the sensitivity of the EMR sensor or like that?
No, there will not be any increase in the sensitivity, but using some different arrangements, instead of getting one revolution or one cycle of sine and cosine, you may get multiple sine and cosine. For example, the number of poles will increase.
That will be more effective. No?
Not necessarily, it depends actually. See, for example, that may not be effective actually. Just a second. So whatever the technique which we have discussed, this technique is called as on-axis, okay, where the magnet is present, the center of the magnet coincides with the axis of rotation of the shaft and the center of the IC. Right? There is one more technique by which you can measure. This is called as off-axis. So this is the shaft, this is the magnet, and here you place the TMR IC. Right? So this magnet, if it is having multiple poles, what will happen is you will get multiple rotations or the multiple outputs from the sensor, right? So now, so for a same 360 degree, if I am getting multiple signals, then you have to have additional signals to correctly identify the actual angle, right? Do you understand that? So for example, a single sine curve and a single cosine curve is sufficient to measure the angle up to 360 degree. But now if you have multiple sine and cosine curves within that same 360 degree, you will have to have multiple distinctive signals to differentiate between one angle and the other angle. That is one concern. Okay? So yeah, this is right. As such, I don't see any reason to go for the multiple approaches. Yes. But another beauty of the TMR sensor is, if you want to measure, see, there is a difference between speed measurement and angle measurement, right? So if I want to measure the speed, one TMR sensor will give two outputs, V sin and V cos, right? The frequency of V sin and frequency of V cos is nothing but the speed of the rotating shaft, right? So from one signal you are getting two outputs to measure the speed. So it means that the redundancy is more when you are using a single TMR sensor. Am I clear here? So yeah. Anything else?
Sir, tunneling means what? Term use the tunneling.
Yeah.
What is the meaning?
So tunneling is a phenomenon. You know that the insulators do not carry any current, right? Because of very high resistivity, right? So however, if suppose you have a very small layer of insulation, and suppose here there is a metal, here also there is a metal, right? And if you apply a supply here, okay, so these electrons can even cross this barrier layer if the amplitude of the waveform function, if you have studied this basic physics, exceeds certain level. It means that if you apply a sufficiently high voltage, it can literally tunnel or cross this barrier layer. This is what
breakdown.
Not breakdown, not necessarily breakdown. Breakdown means I mean,
But
breakdown is
conducting part.
totally different. Okay.
Conducting path
Yeah.
is created.
So here the electrons, since the insulation layer thickness is so small and the amplitude of wave function of the electron is sufficiently large to cross this one. If you have studied about the probability, if the probability of having the electron at one particular position in the insulation decreases exponentially with the wave function. So if the amplitude of wave function is high, you will have high probability that the electron can be there in the insulation. Is it clear?
Now we increase the voltage like this in this system.
Yes, yes. So if you increase the voltage, can pass through. Okay. Anything else? Thank you very much.
Thank you, sir.
I'm thankful to sir for giving me the opportunity to share my knowledge. I hope you have liked it.
Thank you.
Thank you, sir, for a wonderful speech. Now I request our coordinator, Professor Sumit Banerjee, sir, to give a small token of appreciation from our department.